In this video, I will demonstrate how to perform a one-way repeated measures ANOVA. Now, this type of ANOVA is used when we have repeated measures, in other words, the same group of people being measured multiple times, or the same group of people perhaps being subjected to several different treatment options or protocols and then measured on the outcome. But this is the extension of a dependent samples or paired samples t-test. In the dependent or paired samples t-test, we're comparing two sets of scores that are often repeated measures or a crossover design. But with the one-way repeated measures ANOVA, we're comparing three or more time points or three or more outcomes that we've measured on the same group of people. So it's handled in much the same way. Many of the assumptions are the same, including that the outcomes need to be normally distributed. And so what we're doing, much like the standard one-way ANOVA, is we're going to do a two-step process here. We've got an omnibus test that's going to tell us if there are significant differences somewhere among the three groups. And if there are significant differences, then we'll do a post hoc to determine which pairs of time points or which pairs of groups of scores are different from one another. So in this case, we've got 3 time points, 3 measurements on an outcome. We've got a pre-measure, we've got a post-treatment measure, and then we have a follow-up measure. And what we want to see is, are there changes over time? And if there are there differences between the time points in the amount of change that we're seeing? So our null hypothesis in this situation would be that the mean of the pre-score, number 1, is equal to the mean of the post-test score is equal to the follow-up score. So that's our null hypothesis, and we're going to test that hypothesis using a p-value of 0.05. And because, again, we're doing a two-step ANOVA process, our error of making a hypothesis testing error will stay at 5% from the omnibus to the post hoc. So let's go ahead and see how we would run this. So we're going to go to our analysis menu. We're going to find our ANOVA menu, and we can see here repeated measures ANOVA. We're going to click on that. And we essentially just have to add in our dependent variables. And typically we want to enter them in the order that they occur. So in this case, our pre-test 1 occurred first, then our post-test 1 occurred, and then our follow-up test number 1 occurred. And so that way we can see that temporal order. If we're doing a crossover design, the order doesn't matter because that's usually randomly assigned, so you can enter the variables in any order if you're doing a crossover type of design. So once we have our variables entered in, again, you can do 2 or more. You can do 4, 5, 6 if you want. Theoretically, there's not a limit to that, but the more you do, the more complex, obviously, the interpretation becomes. So we've got our 3 time points entered here. We're going to go ahead and click confirm, and then we go ahead and click calculate. And we can see here we've got an interpreted output, but we're going to look at the raw output so we can actually see the tables that we're interested in. So the first thing we want to look at is the model results. And what we're looking for is the within factor row that's going to produce an F score for us and a p-value and also an effect size value, which we'll look at here in a minute. But we can see here the within factor F score is 13.07, which produces a p-value that is much less than 0.05. So this is the omnibus test portion, and so this is telling us, because this p-value is less than 0.05, it's telling us that there is a significant difference among the 3 time points somewhere. We don't know which ones are different yet from each other, but we know there is a difference somewhere. And we can see here the effect size value produced here for us, which is partial eta squared. That's a 0.466, and that is considered to be a large effect size. Anything greater than a 0.14 is considered to be a large effect, and so we've got a large magnitude of effect here. So we have statistical significance somewhere among our groups, and we also have a large magnitude of effect. Now what we can do next is look at the means table, and we can see the mean values for each of our 3 time points. And we can see the mean value for the pretest was 3.8, the mean value for the post-test was 5, and the mean value for the follow-up is 6. So there's definitely numeric differences here, but we don't know if these differences are statistically significant yet. And that's what we're going to look at the post hocs to help us do. And that's what this last table demonstrates, are the post hoc comparisons between each pair of time points. And so we can see here in the first row, we've got the pre-test compared to the post-test. And what we see here is the mean difference between those two groups of scores. And then we have a p-value associated with that. And we can see this p-value is greater than 0.05. So we can conclude the mean difference between the pre-test and the post-test is not significantly different. Now the next thing we can look at is the pre-test compared to the follow-up. And we can see there's a mean difference here of 2.25. And if we go all the way over to the right, we can see the p-value associated with that difference is statistically significant. So there is a statistically significant change from the pre-test to the follow-up. And the last comparison we can look at is the post-test compared to the follow-up. And we have a mean difference of 1, and we can again see the p-value is not less than 0.05. So the difference or the change from the post-test to the follow-up is not significantly different. So at this point, the conclusions we can make are that there is a significant effect of time from our pre-test to our post-test to our follow-up, and it's less than 0.05, and it's a large magnitude of effect. But as we dig deeper, we then conclude that the only pair of scores that are significantly different from each other is the pair of scores from the pre-test to the follow-up. So there was not a significant change from pre to post, but there was from pre to follow-up. And there was not a significant change from the post-test to the follow-up. So the majority of the change, significant change, occurred from the pre-test to the follow-up. And we can see that the score, as we look at the means, we can see that the score increased steadily as time progressed. So the score from the pre-test to the post-test, the follow-up, increased by almost 3 points. And that difference is statistically significant. So hopefully you found this to be a useful explanation of this technique, and good luck using this technique in your own research.